Students, hello students, welcome back. Now let's continue the latter part of the chapter. In the last class, we have discussed about the unit cells. Okay, in the last part we have discussed about the unit cell. What was the unit cell? The smallest possible portion of a part of crystal lattice which repeats itself in different directions of all the lattice is called the unit cell. Okay, which means that if I am considering this cubical crystal lattice, okay, you can see here this is the cubical crystal lattice of a particular metallic sorry, not a metallic, of a particular uh, crystal, okay, of a particular crystalline solid. Here, if I am taking this red colored points, these are the crystal lattice points. Okay, lattice points, it means that these lattice points are denoting the position of the particles which constitutes this crystal. Okay, now taking the consideration for a single part of this crystal lattice, okay, single part of this crystal lattice, it means I am considering this single cubical structure here. Okay, I am marking it with red color. This small cube, if I am taking from this large cube, then this small cube, if I am repeating this small cube in the upside, in the downside, in its left side and its right side, like this, repeating the same cube again and again, I can form this large cubical lattice. Okay, so hence this lattice, this single cube is called as unit cell. Okay, we will call it as unit cell. And the unit cell for a cubical lattice is always a cube. Okay, many different shapes of unit cell can be formed out. We will study them later. Now, what are some of the characteristics of unit cell? The unit cells have three edges. Okay, here you can see the three edges of unit cell. One is this, and the other one is this. Okay, three edges are there. So now, if I am naming these edges like A, B, and C, three edges are being named out like this: A, B, and C. Now, sorry, these three edges will be having angles also. Okay, they are making some angles with each other. So if I am taking in consideration that opposite to A, it means angle between B and C, it will be considered as alpha. Okay, opposite to B, it means angle between C and A, it will be beta. And opposite to C, it will be angle between alpha and A and B, that will be gamma. So these are some of the parameters by which we can define a unit cell. Okay, by which we can define a unit cell. So what are they? First, the edge distances or the edge length, which is denoted by A, B, and C. Okay, now the angle between these edges, that is alpha, beta, and gamma. So the parameters by which we can define them are A, B, C, which are the edge length of the unit cell. Okay, and alpha, beta, and gamma, which are the angle between edge lengths. Now, since it is a cube unit cell, cubic unit cell, okay, since it is a cubic unit cell, so here it is easy that to say that all the edges will be of same length. It means if I am considering this edge as A, then all the three edges will be of same length, which will be A. And also the angle between each edge will be perpendicular to each other. They all will be perpendicular to each other. So therefore the alpha will be is equals to beta is equals to gamma is equals to 90 degree here, because it is a cube. And also A is equals to B is equals to C is equals to A here. Okay, for a cubical unit cell I am talking about, different unit cells will be having different parameters for all these things. Okay, means edge length can be different and the angle between the edge length can also be different there. These things are used to define our unit cell, to represent our unit cell. Okay, let's move further. Now after the characteristics, I want to take your attention towards the types of unit cells. Okay, how many types of unit cells are there? Majorly two types of unit cells are there. Majorly two types of unit cells will be there. One is the primitive unit cell and the other one is the centered unit cell. Okay, primitive unit cell and centered unit cell. Two types of unit cells are there. In the primitive unit cell, first let's talk about primitive unit cell. Okay, what is primitive unit cell? So the unit cell in which the constituent particles, which can be atoms, ions or molecules, okay, they can be atoms, ions or molecules, are located only at the corners of the lattice. Okay, they are located at the corner of the lattice is called a primitive unit cell. Okay, when we will find that particles the particles which are constituting our crystal, all the particles are present only at the corners of our lattice. Okay, only at the corner of our lattice, then it is called as a primitive unit cell. Then it is called a primitive unit cell. Every atom at the corner is shared among 8 adjacent unit cell. Okay, here we will see that each corner is been shared here with 8 adjacent unit cells here. Okay, next there are 4 unit cells in the same layer and 4 in the upper or lower layer. Okay, you will see that there are 4 unit cells will be seen in the upper layer and 4 will be seen in the lower layer. Not unit cells, this will be particles. Okay, this will be particles or points, lattice points. Therefore a particular unit cell has the only 1 by 8th of the atom. If I am considering how I can make you easy, let's take 1, okay, then 2. Hmm, this one circle shows a particle, second circle shows second particle, third shows third particle, and the fourth shows fourth particle. Okay, similarly at the back of it more 4 will be there. Okay, same like 4 more will be there. 1, 2, 3 and 4, like this. Okay, I have messed it up. You can easily understand in the in the next slide. I will show you how it is been using here and how 1 by 8th of a single atom is been used out here. Let's take here only. If I am taking one here, the next is here, the next one will be here, next will be here. Okay, and all these are connected together. Okay, all will be connected together. The lattice point is the representation of these atoms or is of these ions or of these molecules as their center points only. Okay, they are generally very big and they touch each other. Okay, so here we can see that only 1 by 8th part of per atom is being used out here. You can see here 1 by 8th part of your atom is used out here. Only 1 by 8th part. Like this, only 1 by 8th part will be used out here. Means out of 8 atoms or out of 8 particles, only 1 by 8th of their parts are being used, which are constituting a primitive cell. Okay, which are constituting a primitive cell here. Each small sphere represents the center of a particle that occupies that particular position and not its size. Okay, as I have told you before, that these small spheres are representing only the center of our particles, okay, that occupies that particular position and not its size. I am not depicting these points as their size. They are very large in shape, okay, they are very large in shape. This structure is known as an open structure. This type of structure is also known as an open structure, okay. The atom in the primitive cubic cell are present only at the corners. First, the characteristics of a primitive unit cell, okay. So in the first characteristic, you know that all the particles in a primitive unit cell, in a primitive cubic unit cell, will be present only at the corners, okay. They will be present only at the corners only. Next, every atom at the corner is shared among 8 adjacent unit cells, okay. It means that this one atom will be shared with different 8 unit cells, okay. Like this, different 8 unit cells will be there, which will be sharing this single atom. It means that each unit cell will be having only 1 by 8th part of it, okay. Each unit cell will be having only 1 by 8th part of a particle, okay. It means that one atom or one particle is being shared with 8 different unit cells, okay. 8 different unit cells it is been shared, okay. Let's move further. Next characteristic, it is that 4 unit cells are present in the same layer. In the same layer, how many unit cells will be present? 4. How? 1, 2, 3, 4. If I am considering it a single plane, then here how many unit cells will be present in the same plane, in a same layer? 4 unit cells will be present at a time, okay. Next, therefore a particular unit cell has the only 18th of an atom, okay. Only 1 by 8th of an atom, sorry, it is 18th, not 18th. 1 by 8th of an atom, 1/8th part of an atom. Each small sphere in the following figure represents the center of a particle which occupies that particular position and not its size, okay. Now, in each cubic unit cell, there are total 8 atoms. So therefore, the total number of atom in one unit cell, okay, how to calculate the total number of atom in one unit cell? So if I am saying that how many number of atoms in one unit cell, which unit cell? Primitive unit cell, okay. How many number of atoms are there? 8 number of atoms are there. Then the total number of atom in unit cell, total number of atom in this unit cell will be 8 into one atom is contributing its 1 by 8th part only. So therefore 8 and 8 will get cancel here. And how much of atom is there, or how much of particles is present there? Only a single particle is contributing in a primitive unit cell, okay. Only a single particle is contributing in a primitive unit cell, okay. Let's talk about the centered unit cells now. What is a centered unit cell? Let's talk about it. So as you are cleared about primitive unit cell, let's move towards the central unit cell, okay. So in centered unit cell, as from its name only we can see that a centered word used here. So it means that here the 8 particles will be present at the corners. 8 particles will be naturally present at the corners, but some of other particles will be present, or which will be centered at different positions of the lattice also, okay. Means other than the corner position, we can see the particles at some other positions also. So here there are total 3 types of centered unit cell, okay. How many types of centered unit cells are there? Total 3 types of unit cells are there. Centered unit cells are there. First is the body centered unit cell. Body centered unit cell, it is abbreviated as BCC unit cell, okay. Body centered unit cell, or BCC, body centered cell, it is abbreviated as BCC, okay. Next is the face centered unit cell, it is abbreviated at FCC, okay. It is abbreviated as FCC. Next is the end-centered unit cell, ECC. Okay, ECC. Body-centered unit cell, BCC. Face-centered unit cell, FCC, and end-centered unit cell, ECC. These three types of centered cells, unit cells will be shown here. Let's first discuss about the body-centered unit cell. Okay, so by the diagram here you can see here eight eight of the particles are present at the corners. Okay, eight of the particles are present at the corners, and one more particle is present at the center of this lattice. Okay, one more particle is present at the center of this lattice. Okay, so this type of unit cell in which eight corner atoms are present, or eight corner particles are present, and one particle is present at the center of the body of this lattice or this unit cell. This type of unit cells are known as body centered unit cell. Okay, this type of unit cells are known as body centered unit cell. Now let's calculate how much number of contribution, how much contribution of atom has been done here. So to calculate, the simple way we have calculated for primitive cell only we will use here. So how much number of total atoms are contributing here? Total number of atoms contributing here are 8 plus 1 is equals to 9 numbers of particles are contributing here. And how much contribution is there of the total number of particles? So here 8 particles are contributing their 1 by 8th part. Okay, and the one particle which is present in the body, it is contributing his full one condition. Okay, this fully is present at the center of this lattice, therefore it is fully contributing his whole atom here. So hence the total number becomes 2 atoms. It means that total 2 atoms are contributing here in the body centered cubic cell. Okay, body centered cubic cell or body centered unit cell. Okay, let's move further and see the next type, which is FCC, face centered cubic unit cell, FCC. Okay, a FCC unit cell contains atoms along the corner lattices 1, 2, 3, 4, 5, 6, 7, and 8. Okay, 8 atoms or 8 particles are present at the corners. Now each face, so if you see a cube, there are total 6 faces. Okay, so each faces will be contributing one atom here. So 1, 2, 3, 4, 5, and 6. It means 6 atoms are contributed on the faces also, and 8 atoms are contributed at the corners. So how to find out here how much atoms are being contributed here? So for that, for each for the atoms present at corner, how much their contribution is there? Their contribution is 1 by 8 into 8 plus at face the atoms which are present or the particles which are present, they must be halfly contributing to this single unit cell. Half of their will be contributing to the other unit cell to which they are connected. It means that this face is connected to other unit cell. This face is connected to other unit cell. This face is connected to other. This front one is to other. Like this, total 6 unit cells are contributed here by this single face centered atoms. Okay, so it means that half they are contributing in the other unit cell and half in this. So it means that 6 into 1 by 2. So now how much will be there? 1 plus 3, it will be total 4 atoms or 4 particles are contributing in a FCC. Okay, how much of atoms are contributing here? 4 atoms are contributing here. You can see here 4 number of atoms are been contributing here. 8 at the corner and 1 by 8th. The contribution here is 1 by 8th. Okay, the contribution here is 1 by 8th. 1 by 8th. So it will be 1 atom 1 by 8. Face center, for face center it is 1 by 2. So it will be 3 atoms. So total 4 atoms are there. So thus they are having how many? They are having 4 atoms. Okay, they are contributing 4 atoms. Let's move further and see the next type, which is the end centered unit cell. end-centered unit cell. By the name only, you can make an idea there that the 8 atoms will be present at the corner only. Okay, 8 will be present at the corner. 1, 2, 3, 4, 5, 6, 7, and 8. Like this, 8 are present at their corner only. But two of the atoms are present at the two of the end faces. Okay, one end face like this, the upper one, and the other one is the down. Okay, so this type of cubic cells, unit cells, are known as end centered cubic unit cell. Okay, end centered cubic unit cell. So here how we will calculate the total contribution. 8 into 1 by 8, it will be one atom. It means that all the corner 8 atoms, one atom is contributing 1 by 8th of its part in this unit cell. So total 8 atoms are there. So the total contribution by the corner atoms, it is 1 atom. And these two atoms are contributing half of their atomic part in a single unit cell. So it means that one atom is being contributed them by them. So the total atom contribution here is for two atoms. 1 plus 1, two atoms contribution is there in case of end-centered cubic unit cell. Okay, let's move further. Now, as you have seen there that in simple cubic unit cell, how much atom was contributed? Only one atom was contributed. Then in body centered, two atoms was contributed. In face centered, four atoms was contributed. And in end centered, again two atoms were contributed per unit cell. Okay, this number of atom is for per unit cell. Now let's move further and see some examples. Okay, see some examples for each type of unit cells and how much of the particles are being contribution is there. So for a simple cubic, how much how much contribution is there? It is 8 into 1 by 8, which is equals to 1 atom's contribution. Okay, next, how 1 by 8 is contributing? So you can see here that one atoms only 1 by 8th part is being used up here for a single unit cell. Like this 1 by 8th part, how many of them are? 1, 2, 3, 4. Okay, 1, 2, 3, 4. Below here 5. This back one 6, 7, 8. Okay, so here 8 into 1 by 8. So total these 8 parts will contribute, they constitute a single atom here. Okay, this all will constitute a single atom here. Next, for a simple cubic arrangement, let's take an example for polonium. Okay, polonium, one of the atom which you can see here for polonium crystal, polonium crystal. So the polonium crystal is looking like this, where 8 polonium particles are present at the corner of this cube, and they are forming a simple cubic arrangement here. Okay, simple cubic arrangement, and each atom is contributing how much? 1 by 8. So total one atom is being contributing here in its one unit cell crystal. Okay, let's move further. Next is the body centered example. Okay, body centered, how much atoms were contributing here? Two atoms were contributing here. Okay, how the two were there? 8 at the corners mean one atom here, and one at the center mean one atom here. So 1 plus 1, two atoms were totally contributing here. Next, here you can see how two were contributing 1 by 8th here. So 1 by 8th. So 1, 2, 3, 4, 5, 6, 7, and just back this below and beneath the third one, there will be a eighth one also. Okay, and one is being contributed at the center. So here, how much contribution is there? Total 1 plus 1. Total 2 atoms contribution is present here in the body centered cubic cell. Okay, body centered cubic cell. 2 atoms contribution is there. Here you can see the example of cesium chloride or cesium bromide. Okay, where cesium is the center atom. Okay, cesium is the center atom, and chlorine are taking the end corner positions. Okay, chlorine is taking the corner positions here. How this how this contribution is calculated, we will see in the further lectures. Okay, I will let you know how this percentage has been taken out, that how much of the space is being used in which type of cubic lattice. Okay, we will see this in the further lectures. There is a proper formula for this which will be used. Next is the face centered cubic cell. So here 8 corners. Okay, 8 corners. Let's take the next slide. There it will be easy to see. Okay, 8 corner atoms. So one, two, three, four. Okay, five, six, seven, and just behind this eight one is there. Okay, 8 corner atoms, and 6 space atoms are there. How 6 space atoms are there? See, one, two, three. You can see here the fourth one, then beneath fifth one, and here this is the sixth one. Okay, so here this is the face centered cubic cell. For which kind of examples are there? NaCl. So here this blue sphere is showing Na plus, and this red sphere is showing the Cl minus ions. They are sorry, they are taken together here to form this lattice. Okay, let's move further and take another example. Next is the end centered cubic cell. Here in end centered cubic cell, what will be there? There will be 8 corner atoms. One, two, three, four, five, six, seven, eight. Like this, 8 corner atoms are there, and two face atoms will be there, which will be present at the end faces. Okay, it means they will be parallelly to each other. They will be situated. Okay, not like this, that one is situated here and one is here. No, not like this. They will be parallelly situated on the parallel faces. They will be situated at the parallel faces. Therefore, they are called as end-centered unit cells. And how much contribution is there? Here also, 2 atoms contribution will be seen out here. So the maximum contribution is been seen in the face-centered cubic cell. Okay, maximum contribution is seen at the face cubic centered cell. Now, if I am taking the values for the radius, okay, for the radius here, then for cubic simple cubic cell, the radius r, which is the r, this r means the sphere's radius. Okay, that sphere's radius, it is taken as a by 2. Okay, it is a by 2. It means that in simple cubic cell, the radius of the sphere will be is equals to the half of the edge length. Okay, half of the edge length. While in case of face center, it will be is equals to a upon under root 8. The radius of the sphere will be equals to a upon under root 8. While in case of body centered cubic cell, it will be under root 3 into a upon 4. Under root 3 into a upon 4. It will be like this. Okay, these are the r's value or radius value for each cubic unit cell particles. Okay, particles constituted there. Next, some formulas are there. The first formula is the relation between the relation between the radius, coordination number, and the structural arrangement of the molecule. Okay, this is known as the radius ratio. So what is the radius ratio? The radius ratio is equals to the radius of cation upon radius of anions. In the previous, I have seen that I have shown you that Na plus and Cl minus was constituting the lattice there. So by taking out the radiuses of the cation and anion and dividing both of them, we can get the radius ratio here. Greater the radius ratio, what is the relation between them? Greater the radius ratio, larger the size of the cation, it means that more the radius ratio, more the bigger the cation will be there. Hence, the coordination number will be higher there. Okay, greater the higher coordination number will be there. Okay. Now, next is the density. Okay, next is the density. So the density's formula is taken out here. Z is equals to m into ma upon na into a3, where Z is equals to number of atoms, how much atoms are been contributing in that particular unit cell. Then Ma is the mass number of that particular atom. Okay. Next, Na is the Avogadro's number, and A is the edge length or side length, or the edge length. I have told you about the edge length here. Okay. Next, we have talked about how, as you have studied the structures in the class 11th. Okay, in valence bond theory, you have studied about the structures now. So now let's see how the structure analysis can be done by radius ratio rule. Okay, how it can be done by. First, 0.02, sorry, 0.02, 0.155. If the radius ratio is between 0.02, 0.155, then the coordination number will be 2. Then the coordination number will be 2, and the shape will be linear, and the example is HF, Next, from 0.155 to 0.0225. Okay, 0.155 radius ratio to 0.225 radius ratio. Here the coordination number will be 3, and the shape is trigonal planar. Okay, triangular planar. It will be triangular planar. Yeah, if you remember that, like this, it will be the shape like this. This was the triangular planar, where each triangle side, each vertices were denoting a single particle. Okay. Next, next is the 0.225 to 0.414. Okay, here the coordination number will be 4, and it will be a tetrahedral. Means a single atom is being connected with the 4 different atoms there. Okay, a single atom is being connected with the 4 different atoms there. This is known as a tetrahedral structure. And for that, the radius ratio must be between 0.022 to 0.414. Next, 0.414 to 0.732. Okay, so here the coordination number will be 6. It is a octahedral shape. Means like this: 1, 2, 3, 4, 1, 2, 3, 4, like this. This is the octahedral shape, where 8 atoms will be connected to the single central atom. Okay, 8 atoms will be connected to the single central atom, like this: 1, 2, 3, 4, 1, 2, 3, 4, like this. Okay, this is the octahedral shape here. Next, 0.732 to 1.0. 0.732 to 1.0. It is the coordination number 8, which is the body centered cubic unit cell. Okay, which is the body centered cubic unit cell. One example you have seen before only, CSCl. Okay, CSCl. Octahedral shape is for NaCl. The tetrahedral shape can be seen in ZNS and silicates. Okay, and the triangular shape can be seen in borax and boron nitrate. Okay, so these were the relation between the structure, coordination number, and the radius ratio. The higher the radius ratio, the higher is the coordination number, and the complex the shape will be there, Next, for Bravias lattice, let's talk about the Bravias lattice. So in Bravias lattice, there are total 7 type of crystal lattice will be there. Okay, how many types of crystal lattice will be there? 7 type of crystal lattice are there generally. But in Bravias lattice, there are total 14 type of crystal lattice are present. Okay, there are total 14 types of crystal lattice are been defined in the Bravias lattices. And The unit cell parameters by which the previous lattice are been defined, they are the edge length A, B, and C, and the angle between this edge length alpha, beta, and gamma. Okay. So let's define what are the Bravias lattice and see what are the different 14 Bravias lattices which we have to study in our course. The first, cubic cell. Okay, the first is the cubic cell where A is equals to B is equals to C. It means all the edge length will be equal to each other. Here all the angles will also be equal to each other, which will be equals to 90 degree. Which type of Bravias lattice you can see this type of conditions? One is the simple cubic cell, in face centered cubic cells, and in BCCs. So three types of Bravias lattice can be seen here. How many symmetrical elements are present there? So it will be uh, 3 axis folders and 4 axis fold. Two types can be there. 3 fold axis. Okay. How many 4 types will be there, and 4 axis fold here? 3 types will be there. Next is the orthorhombic. It is the orthorhombic where A is not equals to B is not is equals to C, and angle are here 90 degree, but the angle are here 90 degree. Here 4 different types can be seen: simple cubic, face centered cubic, body centered cubic, and face centered cubic. Okay. How many axes, symmetrical axes are there? Two-fold symmetrical axis will be seen, and they will be of 3 types. Okay. Next is the tetragonal. Tetragonal where A is equals to B, but B and A is not is equals to C here. Here alpha and beta and gamma will be is equals to 90 degree also here. Here two types will be seen: simple cubic cell can be seen and BCCs can be seen here. And it is only a four-fold axis symmetrical. Only one type of four-fold symmetrical axis can be seen in tetragonal system or tetragonal cubic cell. Okay, Bravias lattice. Next is the monoclinic. Next is the monoclinic where no edges will be equal to each other, no edge length will be equal to each other, but alpha and gamma will be is equals to 90 degree, and beta will be different from the 90 degree. Beta will be different from the 90 degree, and this type of cubic cell will be called as monoclinic cubic cell. Which types of cubic cell will be containing this? Simple cubic cell can be containing this, and end face centered can be containing this. Okay. Next, how many fold axes are there? Two fold axis symmetry can be seen out, and that will be only of one type. Next, triclinic. Here no side will be is equals to, and no angle will be equal to 90 degree. These can be seen only in simple cubic cell, and here one fold axis is of only one type is present. Next is the hexagonal. Okay, hexagonal close packing or hexagonal Bravias lattice. There A is equals to B, but it is not is equals to C. Alpha and beta are equals to 90 degree, but gamma is equals to here 120 degree, and it is present only in the simple cubic cell type, and 6 fold axis are there, that is also of one type only. Okay, 6 fold axis are there, that is only of one type only. Last is the rhombohedral or trigonal. Okay, last is the rhombohedral or trigonal where A is equals to B is equals to C. All the edge lengths are equal, but alpha and beta are equal to 90 degree, but gamma is not equals to 90 degree. This is also a simple cell type, and three-fold axis are present, that is only of one type only. Okay, let's see the pictorial depiction of Bravias lattice. Okay, so some examples are given here. First is the cubic. For cubic, NaCl, KCl, CaF2, Cu, copper, ZnS, zinc sulfide, cesium chloride, copper oxide. All this will be having cubic cell. Okay. Next is the orthorhombic: barium sulfate, potassium nitrate, magnesium silicate, silicite, K2SO4, potassium sulfate, cadmium sulfate, AgBr, silver bromide. Tetragonal structure can be seen in tin oxide, titanium oxide, zirconium silicate. Next is the monoclinic. Monoclinic can be seen in calcium sulfate 2H2O, CaSO4 2H2O. What is this CaSO4 2H2O? This is gypsum. Okay, gypsum salt. And monoclinic S, one of the example. Monoclinic S means sulfur's monoclinic shape. Okay, Next is the triclinic, CuSO4, 5H2O, NaHSO4, H3PO3, hypophosphoric acid. All this will be having triclinic shape, triclinic cubic cells, hexagonal. Hexagonal can be seen PbI2, magnesium, cadmium, zinc, zinc oxide, boron nitrite, silicate, HGS, sulfide, mercuric sulfate, sulfide, all these cadmium sulfide, all these are having hexagonal structure. Rhombohedral or trigonal structure can be seen in graphite, in iodine chloride, in Al2O3, aluminium oxide, okay, calcite, CaCO3, okay, calcite, um, arsenic, antimony, bismuth, all these type of crystals are having rhombohedral or trigonal unit cell structures. Okay, let's see the pictorial depiction of this Bravias lattice. So first, the cubic lattice. Okay, first is the cubic lattice. So cubic lattice, in cubic lattice, three different are there. One is the simple primitive, 8 corner atoms, alpha, beta, gamma is equals to 90 degree, a, b, c are also equal to each other. Here also a, b, c are equal to each other, alpha, beta and gamma is equals to 90 degree, but a single cell will be present at the body center. Okay, and face centered means six atoms will be present at the faces. Okay, and six are present at the faces, and left are present at the eight centered corners. Next is the orthorhombic lattice. Here a is equals to b but not equals to c, means that a and b are same but c is not equal to them. Okay, also alpha, beta and gamma are at 90 degree. Here also four different can be seen out here. One without any centered electrons, means primitive one. Then one body centered, end centered, and face centered. Four different type of orthorhombic lattice can be seen out here. Okay, so now that table will be more clear that that four was for these four types of orthorhombic lattices there. Okay, next is the tetragonal lattices. Okay, tetragonal lattices. Here you can see that a is equals to b but not equals to c, and angle are also 90 degree here, and two types are seen here, one body centered and one simple unit cell. Okay, next the monoclinic. In the monoclinic also a is equals to b is equals to but not equals to c, and 90 degree, all angles are 90 degree, but here only two types can be seen, simple and the end centered. Okay, simple and the end centered, two types of monoclinic lattices can be seen out here. Next is the triclinic lattice. Okay, triclinic lattice where a is not equal to b is not equal to c, all the three edge length are different, but the angle are 90 degree, between them. Okay, this is the triclinic lattice, and only one simple cubic cell will be present here, simple cubic cell will be present in this type. Next is the hexagonal lattice. Okay, hexagonal lattice. So here hexagonal is formed out like this: 1, 2, 3, 4, 5, 6. This is the hexagon. Like this only, here below also hexagonal lattice is formed out here. Like this. Okay. So here also you can see only a single simple cubic one is formed out here. No other type of lattices can be seen out here. Okay. Alpha, beta and gamma are 90 degree here. They are all 90 degree to each other, but the length here ABC is also equal. Okay, length here ABC is also equal, and they are forming a hexagonal shape. Therefore, they are known as hexagonal lattice. Next is the rhombohedral trigonal lattice. Okay, rhombohedral trigonal lattice. Here the rhombohedral or trigonal lattice. Here you can see that a trigonal shape is formed out here like this. Or when you join two triangular shape, a rhombohedral shape, rhombic shape is formed out here. Therefore, it is known as a rhombohedral, because one rhombic shape upside and one rhombic shape downside like this. So it is also a example for rhombohedral, and graphite is one of the great example for this. Graphite, okay, antimony, bismuth, all these are having this kind of crystals and this kind of shapes. Let's move further. Structure of important ionic compounds. Okay, let's discuss about structure of the some of the important ionic compound. First is the NaCl, or we also call it as rock salt. Next is the CSCl and ZnS, zinc blende or sulfurite. Okay, sulfurite. Next is the AB2 type, where CaF2, titanium oxide and silicate oxide we will be discussing. Okay, so for NaCl, this is the cubic lattice for NaCl. Okay, this is the cubic lattice for NaCl. Sorry, cubic lattice for your NaCl. Here, this blue circle is this blue is showing the Na plus. This red is showing the Cl minus ion. Okay, so then you can see Na plus, Na plus, Na plus, Na plus, Na plus, Na plus. 8 Na plus at the corners. Here also 1, 2, 3, 4, 5, 6, 7, 8. 8 at the corners. Okay. So here two different cubes are formed out here. Two different cubes are formed out here. Okay. And that cube can be seen like this. 1, 2, 3, 4, 5, 6, 7 and 8. One cube is like this and another cube is like this. 1, 2. Let me change the color here. 1, 2, 3, 4, and just below this 1, 2, 3, and 4. If I am forming a cube, 1, 2, 3, 4. Okay. This green cube is for your chlorine atoms. Okay, chlorine ions. For this chlorine ion, this green cube is there, and for red one means for Na plus. Okay, this cube is there. So this kind of structure has been formed out here. This is Na plus, Na plus, and this is the Cl minus, Cl minus. Like this structure is there, and they are forming a cubic unit cell here. Okay, they are forming a cubic unit cell here. So here, how many? What is the coordination number here? You can see how many atoms are present at each faces. How many atoms are present at each faces? So the coordination number here, it will be 6 is to 6. Okay, 6 is to 6 coordination number will be there. How we will calculate 6? 1, 2, 3, 4, 5, and sorry, how you will calculate the coordination number here. Okay, so for how much chlorine is present here? How much chlorine is present for corners? It is 8 into 1 by 8 means 1 chlorine atoms is contributing here. Okay, how much face centered chlorine atoms are present? 6 into 1 by 2, 3 are present there. Okay, how much face centered are there? 3 of them are using as a face center. Next, Na at center. How many Nas are there? 12 at center. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 1, 2, 3, 4. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 plus 4. 12 are there. 12 into 1 by 4. They are acting as at centers. So Na is contributing how much? 1 as a body center. See, you can see here at middle one. Okay. So now the total number of Na, how much total number of Na is there? 4. 1 plus 3, 4. And how much atoms are contributing to form here? For chlorine, 1 plus 3, 4. So total 4 Na plus and 4 NaCl are contributing here. So therefore each unit cell will be having how much of molecules of NaCl? four molecules of NaCl will be there. Okay, four molecules of NaCl will be forming a single unit cell for a NaCl. Okay, for a single unit for a NaCl, here it will be forming by four molecules of NaCl. Single unit cell will be forming by four NaCls. Let's take another example for CSCl. For CSCl, you will see that 4Cl, 4Cl, and 1Cl at the middle body center. Okay, four chlorine atoms at the upside, four chlorine atoms at the bottom side, and each of them means this Cl, this CS is being joined with eight of these chlorine atoms. All the eight chlorine atom, it is contributing them. So therefore the coordination number is 8 is to 8. Okay, the coordination number is 8 is to 8. Here 8 is been contributed here, and 8 different CS will be joined up here also. How 8 is to 8? There it will be confusing here. So 8 different CSS are joined with each chlorine atom. Okay, like this. So here, how much contribution is there? Okay, 1, 2, 3, 4, 5, 6, 7, 8, and one CS atom is contributing with 8 different CS atoms, Cl atoms. Okay, so therefore the contribution ratio is coordination ratio is 8 is to 8. Okay, coordination ratio is 8 is to 8. So how many number of atoms per unit cell? It will be one only. Okay, it will be one only. Next, the zinc sulfide. Okay, so here zinc blend or zinc sulfide, it will be having how much? 4 is to 4. Okay, 4 is to 4 because face centered are also there, and the corner atoms are also there. Okay, so here the total contribution of sulfide, it will be 8 into 1 by 8 and 6 into 1 by 2. It means face centered are also contributing by sulfates, and 8 corner atoms are also sulfides. Then the zinc, how much zinc is there? 4 of zinc are there, 4 atoms of zinc are there. So total ZnS, how much it will be there? 4 is to 4, means 4 atoms are contributing for ZnS to form a single unit cell. Next, CF2. Okay, CF2. So CF2 was an example for a AB2 type. Okay, AB2 type means two different layers of AB2 type will be there. So here you can see that Ca 1, 2, 3, 4, 5, 6, 7, 8, 8 at the corner, and 8 cations and 4 anions are there, 4 fluorines are there. So the ratio is here 8 is to 4. Okay, 8 is to 4, and it is a FCC type. It is a FCC type. Next is for Na2O. Next is for Na2O. In Na2O, you can see here Na plus is contributing at the middle, and O2 minus is contributing at the four corners and the faces. Okay, so how many cations are there? Only 4 cations are there. And how many anions are there? 8 anions are there. So the ratio becomes 4 is to 8, and it is a face centered cubic type. Okay, face centered cubic type. Next, in the next class, we will see the structure of important covalent compounds, which is for diamond and the graphite. So I am ending this class here only, and today we have discussed about the different types of cubic unit cells. Okay, means the primitive unit cell and the centered unit cell, and some of their examples has been discussed. So let's meet in the next class.